Hello, hello. Yeah, let's get started. Okay. Yeah, before we get into the content, just a couple of logistical things. Um, I think 7 or 8 out of the 10 teams actually gave me updates. So I think 2 of the teams, if I think they're not here, but I will follow up with them. It's mostly related to the project updates. There's going to be one more sync session, which probably is going to be real time. That we'll do in after next week's lecture. So anyway, that's the logistics. So we are all gearing up for the project component because that's a huge part of the grade, as I mentioned in the announcement in the on Blackboard a couple of times in the past week. So just that's the logistical thing. So we are done with assignments and we are really want to focus on that. And I've already given each individual group like some feedback. Yeah, and if you have questions about your projects, if you're stuck on something, you can reach out to me anytime. Okay. So with that, let me actually talk about what are we doing today. Um, so where are we, right? So we are actually here. Um, uh, so we are pretty much at the final stretch. Actually, there are a couple of lectures left, and since project, as I was saying, right, is a 50%, 60% of the grade. So I am going to meet with each of your teams and ensure that you guys are on track. So what we actually are going to do in today's lecture and next lecture is a transition from all the supervised learning models that we've been seeing to something different. Okay, and today it will be all about reinforcing what that something different is, which is we're going to bring decisions into the picture. In the first lecture, we did talk about briefly about decision making. We're going to bring that back in, and then we'll try to look at prediction and decision making together. Okay, that's the point of that's the focus of this lecture and the next one. Okay, so it's a nice break because right before the previous lecture when we ended, we were talking about unsupervised deep learning, right? So we were looking at GANs and VAEs. Okay, so just to give you a sense of where we were, previous to this lecture is all about unsupervised and supervised learning. In fact, much of the time is spent on supervised learning, CNNs, full power networks, LSTMs, transformers, all of them are supervised learning. We had annotated data or we considered something as the target, next word or whatever. And in the last couple of lectures, we talked about unsupervised learning. So the data is not annotated and we can still learn something from it. And basically a sampler from which we can generate new images, new objects. So that's where we ended last time. So it's a kind of a discontinuity in the sense that this is going to be a new topic. Okay. And let me say what the goals are before we get into some motivation and details. I'll get into that. So yeah. So today, what's the goal? The goal is going to be pretty modest. So we went through all, many of you have done the ML course before, so 575 or 572. So, and then we looked at quite a few advanced techniques. Okay, these models are not easy to train, and you guys saw that in your assignments already, and also you're seeing it in your projects perhaps. But we're going to step back from advanced models like neural network based models like transformers and so on to something which is going to be very basic. Okay? And you'll see that theme throughout this lecture. And it's a foundation for the next lecture, which is all about the concept of reinforcement learning. Okay? We'll introduce what these names mean in a second. But today's goal, by the end of this lecture, you should know what is online learning. Okay. And as I said, the goals are going to be modest, but still it's a transition from thinking about just supervised learning and unsupervised learning. Okay. So that, you have to bridge that gap. Once you bridge that gap, it's going to be very easy to understand decision making and mix of decision making and prediction modeling. Okay, so yeah, by the end of this lecture, what is online learning? How is it different from supervised learning? Okay, and we'll build up step by step. Second thing is obviously there's a relationship between forecasting and decision making, and I will highlight a canonical flow, which is you build a prediction model, just like we've been building in the previous 7 or 10 lectures, and then use the prediction model as inputs to parameterize your decision-making process. It could be an optimization problem, or it could be something else. So it's a two-step modular process. Okay, we will not be talking about that. We'll actually be talking about mixing both today. And so this relation is going to become fuzzy today. Okay, but the baseline canonical way of doing it, which is build a prediction model and then take decisions, is still still a valid thing, but we'll not discuss it today. Okay? The third goal is to know what is the multi-arm bandit problem and few solutions. So actually, we'll spend a bunch of time, 30, 45 minutes, on different solutions to this problem. So it's good to understand what the problem is. Finally, we'll wrap up with another variation of this bandit problem called the contextual bandit problem. And that problem is the closest to supervised learning, but it is not supervised learning. Okay, so you will see pretty much the elements of, okay, feature vectors, outputs. Why are we not just fitting a function which maps from feature vectors to outputs? So we'll see that, and that's the end of, that's the last portion of this lecture. And so those are the goals. So understand what is online learning, what's the relationship between prediction and decision making, and then the multi-arm bandit problem and its solutions, and the contextual bandit problem and a solution for it. We'll get there when we see that. Okay, so those are the goals for today, and next time we'll talk about reinforcement learning. But I will pitch. I'll motivate you a lot about reinforcement learning today. So let's actually jump to the slides. Okay, so I'll get into the layout of today's content in a second. I mean, there are a couple of introductory slides. So from the introductory class, we briefly discussed about decision making, and then we stopped talking about decision making. We were all about making supervised learning more and more, I guess, elaborate, complex by introducing neural network architectures and all the details within. What we're going to do as I said, in the next 2 lectures is to study a way to make data-driven decisions. Okay, data-driven decisions is a very broad umbrella of things you could do, and we'll make data-driven decisions like a company or like a platform. That's the point of view you should take, especially in the presence of feedback. Okay, we make decisions, we get some feedback on how good the decisions are, and then we again make decisions, again get feedback, and so on. Okay, so the lecture today is going to focus on online machine learning, and the next lecture is about reinforcement learning. And after that, if we have time, maybe if we switch the project update meeting to lecture, then we'll look at deep reinforcement learning. Okay, so we're gonna venture beyond prediction. So we'll start with some modest settings. That's one thing. And the second thing that we will not look at, I'm gonna just mention it here because it's important, is that we'll not look at the canonical flow of doing building a prediction model first, and then just focusing on decision making second. Okay, so 2 separate modular steps. You can always do that. I mean, you can always do that in a good chunk of settings, but we'll not talk about that version because that's not super interesting to us. It's a machine learning class, so we want to kind of look at machine learning plus decision making together. Okay, so just a few examples of decision making problems. This is actually a slide from our intro lecture slide as well. Inventory management, right? So observe some current inventory levels and take some actions on how many units of goods of each type to restock, right? So and maybe you take the decision, but that decision has influence on things that transpire over the next, in the immediate future or whatnot, and then you get a reward. Maybe you didn't run out of space, you didn't have to run, make the truck go back, and things like that. So there is some outcome that you care about, some objective, that you care about, and you can kind of set this up as an optimization problem, for example, and solve it. Okay. Same thing with routing. Routing problems are pretty popular in transportation. Many transportation problems kind of boil down to these. For example, if you want to manage a fleet of vehicles, then, for example, which cargo goes to which vehicle, the vehicles, which routes they take, and how to assign, for example, the staff which is going to drive those vehicles given constraints on their driving times. So there are a lot of interesting problems, okay, decision problems, okay, and many of these are driven by numbers in that problem solving process. Those numbers are forecasts. But what we will do, as I said, is look at data-driven decisions or data-driven decision-making setting, especially in the context of when there's feedback available. Okay, and that's broadly under the umbrella. We'll look at one particular, broadly under the umbrella of sequential decision-making. I guess another name for doing this, where you have feedback, make decisions, get more feedback, and so on. And we're going to use the word reinforcement learning here. I'm not going to introduce and define reinforcement learning here, but it's just a motivation that whatever we're studying today and what we'll study in the next couple of lectures, all of that is under the umbrella of reinforcement learning. Okay, it's a nice subfield of machine learning which kind of blurs the boundary between just focusing on predictions and focusing on decisions. Okay, and this is just next few slides are all about just telling you that reinforcement learning is interesting. So this is the list that a magazine called Technology Review put out in 2017. Okay, this was why I'm showing 2017 is going to be important in the next couple of slides. But among the various things that they guessed, one of them was reinforcement learning. Okay, and it's not just although this article is old, there's been a lot of advancements as I'll show in the next couple of slides. So why did they put that over there, right? So why did they say breakthrough technologies of that year, 10 breakthrough technologies? One of them is reinforcement learning, right? So 5 years before that article, right, a group called DeepMind used this reinforcement learning based approach, and behind the scenes actually neural networks, and that's why we're studying in this course, neural networks plus this reinforcement learning solution approach to build a virtual player of these 2D games. These are Atari games. I think we have seen it in the first lecture, perhaps. And they were able to build one specification, one approach, one agent that was able to kind of play these games over and over again and figure out what's the best way to play these games. Okay, so you spend some time, same architecture, same definition, no changing of hyperparameters and stuff like that. Play each of those games for some time, and then that virtual player, was able to beat humans in many of these games. Okay, we'll see this study in detail when we talk about deep reinforcement learning. So this happened 5 years before. Okay, and then 1 year before that news article, that magazine article, this event happened, which is also shown in this cover page of a scientific, outlet called Nature. And so this event was about the software playing against the then rank 1 player, Lee et al., in the game of Go. Okay, so they're playing the game of Go. It's a board game. I think the picture is here in this illustrative figure is here. So it's very similar to chess or any of these board games that you're aware of, where there are 2 players, and one of the players is going to win based on some rules, predefined rules. And until that time, humans were better than computers. Okay, so this game, it's a deterministic game. There's no stochasticity, but it was very hard for computers to figure out, okay, which move to play so that eventually my probability of winning, eventually I win, and which move to make now so that my probability of winning is, as high as possible. Okay, so the computers were not that good at that till that time. They were actually, slowly improving, but the solution that really defeated the player 4:1 in a 5-game series relied on, very intricately relied on reinforcement learning concepts. Okay, and so that probably led to, I'm just hypothesizing, that breakthrough technology magazine screenshot that we saw. Okay, but that's several years ago. 2 years ago, there was this landmark paper by OpenAI, which, as you guys know, has ChatGPT and GPT-4 offerings today. So they had a paper where they showed how to fine-tune large language models. We have already seen some fine-tuning techniques, transfer learning, fixed feature extraction. We also saw LoRa in the class. But there's a way to further fine-tune language models. So these models are already predicting next token, like here on the bottom left side. They're already kind of trained. These neural networks are already trained. Transformer architecture, actually. right? So they're already trained to predict the next token. And then what they want to do with fine tuning is something we've not covered previously because we were mostly focused on other architectures, is that they will use this model, have a bunch of prompts, produce a bunch of outputs. Okay, so for each prompt, the model can actually not just generate one response, but multiple responses. How can it do that? Remember, we talked about beam search decoding and variations where you can generate a output by just picking the top most probabilistic, so the word with the highest probability while decoding, right? That would be the bunch of words with the highest probability one step at a time. But instead, since you have a distribution of words, you can sample from the distribution. You'll get the first word, then feed it in this next decoding step. You'll get a distribution of words, again, sample from that second set of the second distribution, and you get another word and so on. So you can actually generate multiple responses. And if you played with OpenAI's API or Anthropic or any of these, programmatically, any of these language models, there's this parameter called temperature. Typically, they call it temperature parameter. And if you change it to move away from 0 or one of these boundary conditions, outputs will not be the same every time. Like you call the same prompt, call it twice, you'll get two different responses. Okay. So here, what they said is to fine tune. Let's pick this such a language model where if you put a temperature value different from 0 or 1, then you can actually get multiple responses. Somehow get use those multiple responses for the same prompt, order them, get an order relationship between them by saying, okay, one response is better than the other. And how do you order them? You actually ask people. You ask people, hire a bunch of people and say, hey, here are 5 responses from my LLM. And is the first answer better than the second answer, or second answer better than the fourth answer, and so on. You ask them. Okay. Here they're talking about L rating and so on, but just think of it as an ordered bunch of responses. Okay. And so given that human feedback, now you know that the prompt and the response can be used to build a approximate model, which is called the reward model, which says that, hey, given this prompt, if I gave this fifth answer, fifth in my ranking, then the reward is going to be low. And if I give for this prompt the first rated answer by humans, for example, then the reward should be high. Okay, that's called a reward model or preference model. Okay, so you can build this. This is still supervised learning. So far, we've not really done anything for this fine-tuning process. All we said is we did some supervised learning, got some outputs, used humans to generate annotated data, and then again built a supervised learning model. Okay? But after that, you can use reinforcement learning and this reward model to further fine-tune our initial language model. So we're going to go from initial language model to another evolved model, and we're going to use reinforcement learning and reward. And they did that. In fact, they do that still, probably. I mean, we don't know, it's proprietary information, but so that's still an impactful application of reinforcement learning. Okay. To a couple of more, I would say, textual impactful statements here is that, for example, the Google Maps team. So this is from 2020, actually end of 2023. So just 4 months ago. The head of research at Google, he kind of had a summary of what breakthroughs did we make. Obviously, a lot of breakthroughs were related to supervised learning also, but I've just picked out a couple which are related to reinforcement learning. So one of them is about a variation of reinforcement learning called inverse reinforcement learning, which is all about actually learning the reward function. So something to do with reinforcement learning. They said they're able to kind of use inverse reinforcement learning to kind of improve their Google Maps product. Okay. And the second is a little bit more, I would say, not as widely applicable, but perhaps. But AlphaDev is a reinforcement learning based approach or some system that they developed to speed up computer programs. Okay, it's beyond like speed up in the sense of algorithmic speed ups. So they were able to say that, okay, here's implementation of sorting in C or maybe even assembly, and how can they speed that up? And they used like an RL agent to speed that up by a good factor. It's okay. These algorithms, by the way, these are fundamental algorithms. Sorting is a fundamental algorithm. If you've done a computer science 101 type of a course, so speeding that up is actually a huge impact on a lot of things upstream. Okay, including our sorted function that we call in Python, right? So you can call sorted to sort a list of items. So so that was just to give you a plug on like what's more recent for reinforcement learning. And instead of using the examples from the first lecture, which was I think I showed you guys like the full self-driving video in the first lecture, perhaps. If not, I'll show it during the break. One last example is this, right? So NVIDIA, let's call it I understand. NVIDIA has a this page, and they have a package or a solution called ISAC Gym, which is a physics simulation environment for reinforcement learning research. Okay, so all the improvements in robotics today, actually robotics is a field where doing anything physically is super expensive and hard. These actuators, these motors, they need to be super precise and so on. So it's very expensive to actually experiment with physical machines directly. So you generally start with a simulated world in which you kind of manipulate your robot and see how it works, and especially if it's supposed to be autonomous. Mostly you start with simulation. Same with driving also. So you don't directly drive a car in the real world. You generally go in a simulated world and train your car to kind of understand the environment and drive. So this simulator that they released is a pretty, the key feature is that it's a physics, realistic physics simulator, but it's used actually for, they themselves are suggesting the tagline is for reinforcement research, okay? To kind of learn policies, learn how to make decisions, how can this robot make decisions by interacting in the environment and getting feedback, make decisions, and so on. So it's the same theme. I will repeat that theme over this lecture. Yeah, I'll not show the self-driving stuff now, maybe during the break. I think that's too many examples already. We come back here. Okay, so any questions? That was just a hype for our pitching for reinforcement learning. You guys came late, but what about the others? It's just motivation. So hopefully, it's not as mainstream as, let's say, LLM research, but it is actually for fine tuning at least. But it's behind the scenes technical detail. But it is a very interesting paradigm that blurs the boundary between building prediction models and taking decisions. So it's very interesting that way. So what's the outline for the rest of the talk? We'll look at one more example, but a little bit more detail. That's the first bullet point. And then we'll start with really basic stuff, okay? Where we're not gonna even have, as I said, one of the goals was to understand what's the difference between supervised learning and what we're studying here. But that we'll do that in the last problem, where there's actually, which is the closest in terms of resemblance to supervised learning. We'll go back to the basics and think about forecasting or predictions and decision making in the simplest of settings. Okay, that's where we'll start with something called A/B testing. So many of you might have heard of it. If you've taken 570, you've done 2-sample hypothesis test, and maybe it's linked. But we'll look at A/B testing, then we talk about multi-arm bandits. Okay, so let's start with another example, online machine learning, where first I'll set up mechanically, like what is, just definition that our working definition of what we'll call as online machine learning. Okay, so it's just basically 3 steps in a for loop. So if you write a for loop which has these 3 steps, perhaps you're doing online machine learning. So step 1, optionally observe something. Okay, observe the state of the world. Basically observe what is called a context, or optionally get a feature vector. That's what the step 1 means. Get a feature vector. Okay. If you do get a feature vector, it'll be closer to supervised learning. But if you don't, that's okay. Step 2, take a decision, okay, or make an action, choose an action. It's the same thing. And step 3, get some feedback on how did you fare in terms of your action. So you took an action. How did you fare? Like, did you do well? Did you do badly? Okay, and then keep repeating that. So that's the online machine learning setup. And all interesting part is that you probably want to use this feedback to improve the types of decisions you make. Okay, so that's the key crucial thing we will see in a few minutes. Okay, 15 minutes from now. So what do you want to optimize? Generally, I'm going to say optimize feedback. Okay, feedback is this, but generally think of feedback as, like, for example, if you're an online e-commerce store or a website, then generally the feedback is going to be, okay, purchase of something or spending more time on your website and so on. Okay, so that's why I'm saying optimize feedback, but appropriately, whatever feedback you're getting, or rewards that you're getting, sales that are happening, you want to maximize those sales. Okay. One of the assumptions that we'll make today's lecture, is that our actions, agent is us, the platform or firm which is making decisions, and our actions don't influence future context. Okay. And right now, this phrase may seem a little bit hard to parse, but I will show an example in the next slide, and I'll say what this is. Okay. So let's talk about this application, where I'm just still motivating the online machine learning setup. Okay, that for loop, I'm just gonna place it in the context of this example. So here's a publisher, msn.com, and this is their front page. Okay. So here there are two parties, right? One is the firm, MSN or Microsoft here, and there's users, okay, who visit this website. So what's the loop? The loop is users come to this website with potentially some information, some context. Okay, they may have user profile, they may have some previous history that I would have logged. Okay, but that's optional. But let's say they come with some information. I need to take actions. I, as the owner of this website, as a publisher, I take some actions. I choose some news stories to show. Maybe I'll show all stories related to sports, all stories related to movies. Okay, I make some decision, and then I get a feedback. Okay, user may click the cross button and close the site and move away, or they can click around and spend more time on the website, or they may even make a purchase. Perhaps they're selling something. Okay. So what's the goal for the publisher? The goal is to choose content, take actions, yield some desired user behavior, like more stay more on the website or click on something and whatnot. Okay. What's the assumption? The assumption that Microsoft or as a publisher could make, okay, in this example, they will make it, let's say, is that recommendations to one user do not affect the other users. Okay? Or the recommendations I make to this user do not affect their subsequent visit. Okay? That's what I mean. So in the sense that my actions, what I choose to show now, has no influence on what's the state of this user coming tomorrow. Okay? In the sense that they'll not get influenced by what I showed today. Okay. For example, if I'm showing, as a counter example, let's say I only show sports related articles most of the time. Maybe folks self-select, and then folks who liked, let's say, movies, they stop coming to the website anyway. And then you are influencing future contexts that are, okay, you are saying, okay, future contexts are going to be probably sports related people who are showing up more and more, for example. Okay. That's one way to affect these arriving contexts. Okay. Let's say this is the online machine learning loop, and how do you solve this problem, right? So there is going to be some elements of supervised learning. So in this slide, you might be already like thinking of, oh, there's a user profile or users coming with some context. Let's say there's demographic feature, some history feature of what they did. So there's some information about the user, and there's some information of what articles are available to be shown on the site. And given this feature vector, all you're trying to predict is either maybe what to show, or maybe even directly predict what will happen in terms of like what will the user do on the website. Okay. So that could be a supervised learning problem, right? If you have what's the profile and what happened, okay, that could be a valid supervised learning, setting where you have what's the input and what happened, and you can learn a function which can say, okay, any given new input, what can happen. That's possible, but that's supervised learning. Let's park it aside. So what we can do here is that, and that's why this box is not supervised learning, but it's called online machine learning, is that we get to choose our actions, because this is at the end of the day, whatever models we build, we have to actually just figure out what to show, right? It could be a bunch of movies after sports articles or whatnot, but there's some list of things that we can show, and then the user browses whatever we showed and does something like clicking and staying on the website and so on. Okay, so this is what happens. Any questions here? Okay, so because so just to give a sense of like what is the scope of this size of this setting, right? So at that time, this is like 6-7 years ago, or actually 8 years ago. There's some number of users on this website, on this publisher's website, thousands of requests per second, And what they did is they actually put this green box, the green box that we are going to kind of learn today, at least towards the end, the contextual bandit approach. They put the green box up, and they got a little bit of overhead because this thing is not exactly supervised learning. It's not just a forward pass of a neural network. Okay, they got some extra overhead on their machines, and they're going to update. This last couple of bullet points talking about how they are going to update their behind-the-scenes model. And in that setting, they actually saw with that green box and not supervised learning, they saw a delta in their performance that they were tracking in a, I guess, a metric that they were tracking. This is from a paper from 8 years ago. And they're showing an improvement in clicks. Okay, maybe they're tracking clicks, but they're showing an improvement in clicks. Okay. Yeah, this is 0.2. So I think they're just averaging out. This seems pretty noisy, but think of a horizontal line over here. And they're saying that that's a relative gain that they got. Okay, that's a big relative improvement. Perhaps, I mean, given tens of millions of users on this site. Okay, so what we want to do in the next second part of the lecture or the rest of the lecture is just to kind of unravel that green box. In fact, that green box, I slightly opened it and said, okay, the green box anyway has to make decisions, as in like it has to choose, for example, those articles that I need to show, right? So I have to generate decisions. Okay, it cannot be just forecast of what the user will do. That's kind of not useful. At the end of the day, the green box has to show, make actions. Okay, take actions. And I'm also kind of giving a teaser that the green box needs some source of randomization. In the sense that there's something that it needs to do which is different from supervised learning. In supervised learning, this will be a neural network. It will say, okay, given some profile, generate some predictions or just some rank list of items. We're not doing that. So something different here. Okay? That's all I want to point out in this slide. And this type of online, given that in the previous example, the MSN example, you can think of at least related areas. You can think of the same type of loop if you're doing UI personalization, personalization search results, and things like that. It's the same idea. Okay. Any questions here? No? Okay. So let's start with the first example setting. Okay. As I said, I think at the very outset, I said we're going to be modest. So we're going to start with A/B testing. Okay. Why are we starting with A/B testing? How is it related to online learning? We'll make the connection. Online machine learning. We'll make a connection in a second. So what is A/B testing? So how many of you have heard of A/B testing before? Okay. You have not heard of A/B testing? You have. Okay. Okay, so this is going to be easy. So basically, we want to make a decision. Okay, implement option or action A, or implement option or action B. Okay, after making some observations. And so if you want to do this, then you can use something called A/B testing, which has two parts, right? One is to actually collect the data, which is the instrumentation of this A/B testing process. And then once you collect the data, it's mostly a exercise in statistics. So you have seen that in probably 570. So that's what it is. So I do want to motivate it though, because there are many companies that literally just provide very curated, products which enable A/B testing, and just to show you how hard it is, like, you cannot randomly just set up an A/B test that easily. Like maybe first few tests you will be able to set up and you'll be able to decide between A versus B. But, if you're doing multiple tests, which is what many companies do, then it's hard. And that's why there are like dedicated companies for this. And in fact, what types of companies? I mean, here I'm just talking about tech companies, but there are other situations, other fields actually, where A/B testing or equivalent of A/B testing, randomized control trial is also another way to say the same thing, is also implemented. Okay, so I just added OpenAI to just tell you that every company does this. Okay, so there's no exception. So let's start with some simple example, right? So here are two options. Let's say we had a web designer design like two options, and we don't know which one is good in terms of converting users. The only difference is that there's an extra enter coupon code in the second option. Okay, and we want to decide which option is better, and so we don't know a priori. I mean, which option is better because we don't understand user behavior. Let's say, and so we do an A/B test. Okay, we let user see A, let's user see B, and then we figure out which option is better. So any guesses on which option is better here? B. Okay, so how many for B? 3, 4, 5. 5 for B. And so remaining 4 for A. Indifferent. Oh, okay, one of them is like, yeah, it should be the same. He's saying the same. We don't know the user behavior. I mean, so so by choosing an option, you are thinking of some user behavior leading to better sales and one versus the other, right? Yeah, so it's okay. I mean, you get there are only two options, but he said the third option, which is A is equal to B. But okay, so what is the what happened? So with B, it actually lost a lot of money, okay? Or in the sense that in that collected data, it saw that, okay, for the people who I exposed option B, they did not buy the thing that they were trying to buy. And why is that? Is because perhaps the behavior is that they were going to other sites to collect coupons, and by the time they got distracted and maybe left the cart and whatnot. So it could be various reasons, we don't know. But what we observe is what we observe, right? So we showed both options, and we learned that A is probably better for our, in terms of our execution. So this is just an example. Yeah. So with that, any questions here? I know a lot of people said B is better, but it was A. But that's okay. User behavior is something, if you can't guess, you'll have to try it. So okay, let's just at least informally, like make it a little bit more concrete. So A/B testing is about showing users two solutions. By the way, A/B, I keep saying A/B testing, but it's A/B-N testing. You can have multiple treatments and let's say one control, and you can do a more complex version of this. But generally, A is called a control, just I guess convention, at least in my slides, and B is called treatment. And what we are doing is actually, this is the instrumentation part, like collecting the data. So users come to our site, let's say in the previous example, and we want to partition the users into two sets, where for each arriving user, we're going to flip a coin. And if it lands heads, we're going to send it to option A. And if it lands tails, send it to option B. Okay. And then we instrument, or actually just log what did the user do. And then the next step, phase 2, is actually analyze this collected data. Okay. This collecting the data and deciding which option is better is actually, the whole process actually is one of the best scientific ways to establish cause-effect relationship, in the sense that this decision that you made is what is leading to a improvement in something. Okay? So this decision of you choosing not to include that coupon collection, like text area or input area, is what is leading to some output. Okay, so you can make that type of a claim here, compared to pre-collecting data from an existingly running system, and then trying to make decisions. Okay, there's this huge amount of issues with that, and in fact, that is actually related to our online machine learning setup. But I'll get to that couple of a little bit later. Yeah, so as I said, the phase 2 is just two-sample hypothesis testing. So what is this randomization doing? Just I want to highlight that it's basically breaking kind of the dependency between users' covariates or users' features, and they could be influencing the outcome. For example, purchasing or not purchasing, that is being broken by randomizing between the two options for any user. Okay, so it's basically eliminating our bias. Okay, so by randomly splitting the user, an incoming user, to option A or option B, we are kind of saying that we're kind of dropping, or actually we are breaking the dependency between the user feature and what could have happened. So the only difference between the two options would be because there's an extra coupon text area. Okay, so nothing about the users. And so let's talk about the testing part. Just a brief remark on that. Let's say there's the true effect, okay, true mean effect. Let's say this is the probability of purchase. Let's say so. Some point, say 0.3 here and 0.2 here. Then you just want to figure out from the collected data whether 0.3 and 0.2, the difference is actually significant. Okay, and that's how do you do that? There are many ways. I think the way that we actually we are introduced to is this kind of figuring out a p-value and trying to use the p-value to either reject the null hypothesis or not reject the null hypothesis. But there are other, slightly elaborate approaches. We'll not get into that, where you kind of explicitly talk about what is type 1 error, type 2 error, and control them. Or you can you can abandon the frequentist approach and just talk about what's the probability of the hypothesis 0, which is, let's say, option 1 is better than option 2 given data, and what's the probability of hypothesis 1, let's say option 2 is better than option 1 given data. So you can construct all sorts of things. You're bringing in probabilistic machinery. So you're defining random variables and you're talking about conditional probabilities, right? So there are some details here I'm skipping, but that's not because I don't want to spend too much time on testing right now. But I do want to come back to online machine learning. Okay, so before that, let me just briefly mention the pros is basically that you are relying on data. You're making data-driven decisions. Okay, so this is like, I would say, the canonical simplest situation where you're making data-driven decisions, except you're not really using the feedback. Okay, remember our online machine learning setup? There was a step: observe, take actions, get some feedback, and keep repeating that. And hopefully, you take actions based on the feedback that you're getting. Here, in the testing phase, we are randomly splitting users and getting feedback, but we're not really changing our way of making decisions. We are just going to flip a coin, make the decision to show option A. Flip a coin, maybe take the action of showing option B. Okay, so we are kind of in that loop, except our actions are not informed by feedback collected so far, which is fine for now. And I'll show why that is fine, because it is quite used in the industry. It's also called split testing or bucket testing. And it cannot be a one-time process. You do A/B testing, test something, and then maybe whether it's a blue color theme versus a red color theme, it's a typical example that's given on the website's example there. You can do many tests, okay, one after the other. And there is actually all sorts of complication you can introduce. You can do multiple tests, and then you have to kind of control for the, you have to take care of the fact that you are doing multiple tests. And so many things, yeah. Field experiment, this test is what is deciding what decision you're going to take. Field experiment just means I'm just saying, in fact, very liberally using the word to say that your A/B test is deciding the worth of option 1 versus option 2. That's all. So this is the word that's used in social sciences, right? So field experiment is different from lab experiments. And the difference is basically kind of less control in field situations than in the lab. Okay. Any questions here? Okay, so I want to connect back to online ML, but I do want to mention the cons. Even with the simplest thing, right? You're just randomly flipping coins and exposing option 1 or taking decision 1 or decision 2 randomly. Even that has a lot of bells and whistles to make it work well in real world use cases. Okay. And that's because many of the times the difference between option 1 and option 2 is actually very small. Okay, and if you remember from 570, the smaller the difference between the two options, the sample size needed to kind of know that there is to certify that there's a difference between those two is going to be large. Okay, so you might have to run your tests for a long time, have more users per treatment or in treatment and in control to actually resolve that difference if it is small. Okay, and not just that, it's a very the numbers could be as simple as small as like 3% improve sales in one, or email marketing, let's say 3% open rate in one versus 2.9% open rate in the other one. Is it really is it random? Is it is it not, right? That's the type of issues that we'll face. And talking about online machine learning, so the fact that we collect this feedback but we don't improve, okay, so we don't really inform that while we make actions, is a significant I would say aspect of this approach, A/B testing approach, which we could potentially improve upon. Okay, so what can we improve, right? Let's say there were 10,000 users that were exposed to option 1, option A, and 10,000 users exposed to option 2. And after that, we realized, okay, option 2 is better than option 1, okay, because of just doing our test. But let's say option 2 was significantly better than option 1. Okay, in that case, you you got somehow 10,000 users through paid channels, whatever you paid on Google for AdWords and whatnot, you get these 10,000 people to visit your site, and then you really show them the worst option, right? So you're not, you could have done better by just probably showing option B throughout, but you didn't know that beforehand. That's why you did the A/B test. Is there a way to be adaptive? That's where I'm getting to. That can you be adaptive in your actions by looking at the feedback collected so far? What you lose is that all this hypothesis testing machinery that we briefly mentioned. But what you'll gain is you will, under assumptions, but you will know what the right option is, and also not expose the worst options to the users more than it is necessary. Okay, so that's the key idea that I want to get to. Okay. In A/B tests, basically the prediction and decision making is kind of decoupled in some sense. Okay, there's really no prediction. You're just collecting data, okay, and just getting the mean values and seeing whether they're different or not. And then you're deciding for the foreseeable future, you're going to take one of these actions. Okay? Whereas we're going to start kind of influencing our actions, our decisions, based on our predictions. So our predictions is going to be collected data and some transformation of the collected data. It could be functions in supervised learning case, but here it's going to be very simple, whether the means are different or one mean is better than the other. Okay. And on top of that, the more complex setting comes, but we'll kind of wait for that for some time later. Any questions about A/B testing? Okay, it's a very, very brief informal view to just show that it is the canonical simplest. There's no model, right? You're just looking at empirical stat, like a summary stat on option 1 or summary stat on option 2, and just saying which one is better. So there's one number that you're ascribing to each like the two decisions you could do. You could take, right? You get some summary statistic and say, okay, that's kind of shows me the quality of decision 1. Summary statistic that shows the quality of decision 2, and maybe stats are, one stat is better than the other. Maybe decision 1 is better than decision 2. Okay? So no feature vectors involved. Yeah.
Does it have to be limited to 2 options only? Or?
No, as I said earlier, you could have n options. Not just 3. Like you can have 10 options if you want. Yeah. So you can have 10 treatments. It's just that your tests will not be the 2-sample hypothesis. It will be different types of tests you will build. And yeah, I have seen in my experience, generally folks will not just do two sample tests. Sorry, just not have just the treatment under control. They'll generally have multiple.
So when I was like part of it to start.
Yeah.
So when you like ChatGPT, if you write any response, like it gives you 3 drafts, like when you choose from.
Oh, it gives you, the user, 3 drafts.
Yeah, for any response, like any question you ask. Like,
yes, and you get to choose. Yeah. Well, that is not really, they're not, I mean, they are doing A/B testing on that product for sure. But that 3 responses I was talking about earlier is that an LLM can generate, or these types of products can generate multiple responses. And if they are not sure about the top one, they just show you 3 options, hoping that one of the answers is what you're looking for. And further, they can actually collect data. The reward model I was talking about, where humans have to tell which of the answers is better. So if you actually choose one of the answers, that they will implicitly understand that, okay, one of the answers is better than the other 2, they'll use that data for training. So, but I wouldn't say that is related to A/B testing, at least at the face of it. But for that product, Gemini, as well as Bard, or all these products, they do A/B testing extensively. Yeah. Okay, so then let's actually go to the next topic, which is multi-armed bandits. Okay. For this, I do have animations, but they're on a web page. So we will switch between slides and web page. Let's see. Okay, so as I said, our goals are going to be modest. So we're going to abandon the supervised learning machinery in the sense that we'll not even have feature vectors now. We're only going to look at some sort of summarizing numbers per decision. Okay, so it's like I think that's the simplest setting possible, because you're basically saying, okay, what's the quality of a decision? What's the kind of some sort of a score for a decision? And then if maybe you have 5 decisions or 3 decisions or 2 decisions in the previous example, then hopefully one score is better than the other, and then that's the decision you take. Okay, so no feature vector, no label to predict for now. Okay, even that mixing estimation with decision making is has its own very interesting concepts that emerge. Okay, even there. So A/B testing is an example where you could collect the data, do basically estimation first, and then decide, okay, I'll take A or B later. Okay. Now we want to do something more interesting. So the problem. So I'm going to first define the problem as it's defined in the literature, and we're going to tease it apart from multiple directions. So the multi-armed bandit problem involves the online machine learning loop. Okay, where step one is removed. So there is nothing to observe. Okay. So if you remember the three-step process, observe something, take an action, get some feedback, get some reward. Okay. So forget about observation. So we're not in supervised learning land at all. So we take some action, we get some reward. We take some action, we get some reward, and we keep repeating this. Okay. Even here, if you remember, A/B testing is also follows the same loop. It's just that the take some action is just flip a coin, pick an action. Keep accumulating the feedback or rewards that you get. Oh, okay. So that was A/B testing. Here's so multi-armed bandit problem is exactly the same loop, except there is no feature vector to observe or context to observe. So the multi-armed bandit, the name arises from these machines, these machines, slot machines, where this is an arm of the slot machine that you pull. Okay. To kind of play one turn, and you get some reward. If three symbols line up, then you get a big reward. If they don't, then you lose that money. Okay. So and multi-arm just means like you have multiple of these slot machines. Then you can imagine, right? So these slot machines, what are they trying to what are we trying to set up here? Right? So in real case, let's say this is website 1, website 2, and website 3. Okay. One with no coupon, one with a coupon, the other one red color. Okay. Maybe each one has its own conversion rate of a sale happening. Like maybe the first one is 0.3 probability of conversion happening, 0.2 probability of conversion happening, 0.1 probability of conversion happening. Okay. So that's what these kind of try to symbolize. So if you play an arm, you are taking that action of showing that website version, and with some probability, the user buys something. Okay. So that's what this is illustrating. So pulling an arm is like making a choice, taking a decision. Okay? The step 2 of that online loop. Okay, and you get a feedback in the step 3 of the online loop, which is some measure of success, like okay, a sale happened. Okay? If a sale happened, you get $1 or $10. No sale happens, no dollars. Okay, so that's what this is illustrating. So what is the problem, right? So the problem is as follows. Let's say we have k decisions, the 3 decisions in the previous slide. Let's say we have 3 decisions to make, each corresponding to an unknown distribution. Okay. So every time we take a decision, as I said, there's some probability of sale happening. The probability of sale happening means there's a Bernoulli random variable there, right? So there's a single parameter. That means either sale happens or sale doesn't happen. That means there's a distribution there. The distribution is just a Bernoulli distribution, so there's one parameter. It's like a coin flip, right? Coin flip with 0.3 probability. If it lands heads, I get the sale. If it lands tails, I don't get the sale. Okay, that's what this could be. Okay, there doesn't have to be Bernoulli in general, but in our case, let's say it's a Bernoulli random variable. So this distribution is just one parameter, one number. Okay. Don't worry about the boundedness, but it's not important at this point. At each step of this for loop, so we're going to call this time index. Every iteration of the for loop, the iteration index is we're going to call it time for simplicity. The agent, as in the platform, the publisher, for example, okay, we're going to take a decision, which is pull an arm in figuratively from the previous slide, and we're going to observe a reward. A sale happens, a sale doesn't happen. Based on, let's say, in our case, let's say it's Bernoulli. So we either get a sale done or we don't get a sale done. Okay, and we lose 90% of the sales, as was showing earlier. The objective is to maximize the expected sum of rewards. Okay. The objective is to maximize the expected sum of rewards. So I'm going to interact with the world, okay, where users are coming one by one. Every for loop, there's one potentially new user coming, or it could be the same user, but whatever. So every time iteration, I'm going to play an action, which is show a website, and I will only show a website, obviously, when a user is there, and I get a reward, okay, whether that sale happens or not. And over that, I'll have this interaction many, many times, perhaps throughout the day or throughout the year. And I want to maximize the rewards that I get. Okay. And it's stated in terms of expected sum of rewards, but why is there an expectation? Is because since I'm assuming that there is a distribution over each action that I take, so maybe there's a random variable therefore, and so I take an expectation. The mean of each arm, the mean reward, is what I was talking about. 0.3, 0.2, and 0.1 are the probabilities of getting a sale, and so therefore getting $1. And so the mean of the best arm is just the max of whichever one that is. Let's say the leftmost one without the coupon, for example, right? Let's call that number mu star, that's 0.3. And mu k, which is, let's say, k subscripts the 3 actions that we can take, website 1, website 2, website 3. That's 0.3, 0.2, and 0.1. Okay. Any questions here in the problem formulation? So what we want to do is maximize the expected sum of rewards. These are the expectations of rewards at any given point of time, and any interaction that you can have. And so you want to somehow kind of take the right decisions. Let's say you knew that website 1 is better without the coupon field. Then you keep playing that, right? You keep taking that decision every time. If you knew that a priori, then you would get the best thing what you could have expected, which is you collect in expectation, you have the highest amount of rewards collected over the interaction period. Is that clear or any confusion? Okay. I will show some illustration animation, so hopefully it's not going to be completely boring with the slides. So let's start thinking. So the previous 2 slides are just setting the problem. So there is a bunch of decisions to make. Each decision can lead to some random realization of a reward. And I just want to figure out how I make the decisions so that I can collect the most reward possible over an interaction period. Okay, over a day, or over a year, it could be. Okay. So what we can do is let's think of a couple of strategies, right? Like, at the end of the day, I have to take decisions. Every interaction, every for loop step, I want to figure out, okay, which action to take, right? So I can do a couple of things. Obviously, I did not write the thing which we just saw with A/B testing, which is flip a coin and pick a random action. Okay, that's what A/B testing is doing, right? So every interaction, forget about how much, whether I got better rewards in website 1, I'll just flip a coin. If it says website 3, then just show website 3 as well. Okay. So A/B testing is I didn't write it here, but it's a randomized strategy where it is like uniform, pick a random action. Okay. Another example is a round robin strategy. I take, let's say the first user I show for website 1, second user I show website 2, third user I show website 3, fourth user again I show go back to website 1. In effect, you're really not doing much. I mean, you're again ignoring all feedback and you're just saying, okay, I'm just going to iterate through my options, my decisions. The last one is a pretty bad strategy. You daringly take a decision. Okay, I'm only going to show website 3. Okay, that's going to be pretty bad because you lost a lot of money on the table. Okay, so these are some ideas, right? So for each idea or each strategy, you can evaluate what your performance is. Okay? Why can you evaluate? Because of the way we set up the problem, there is going to be a single best decision you could have taken in hindsight. Okay? If you knew the distributions, there is one single best decision you could have taken. Okay? The distribution with the highest mean reward. Sorry, the decision with the highest mean reward. Okay? Which means that if website 1 was really, really good with 0.3 as the probability of sale is website 2 and website 3, then you should always be playing website 1. You know that's the best thing you could have done. So we can define a performance metric called cumulative regret. All it does is saying, okay, if you have chosen website 1 because that's new star, best thing is to keep website 1 n times, then that's the in expectation what the reward you can get. So 0.3 times maybe 1,000 interactions. That's 300 is the dollar reward that you can get, minus what actually in terms of the rewards. Every round you got some reward. You saw $1, you did not see $1. So that's whatever reward you collected. Okay, this difference, if it's small, it's amazing. You somehow figured out what's the best thing to do, because this is the smallest if you're actually showing the best website. Okay. In fact, this is a bit of a messy representation, a little bit messy because these are random variables. And so sometimes it's better to kind of write in terms of expectation, better in the sense that for some realization you can get some reward, in another realization you can get some slightly different reward, even if you did the same strategy. So you can take an expectation, that's what we write here. So expectation to cumulative reward is a performance number that you can assign to your strategy. Okay, one of these strategies, or the A/B testing strategy of just flipping a coin and picking an action. And so this metric, the lower, the better. Okay. And so the whole effort in this data-driven decision making or online machine learning is to be adaptive, unlike A/B testing, and figure out a strategy so that you can kind of have low expected cumulative regret. Okay. Yeah. Okay, so I'm going to show one strategy, and then I'll show some animation so that, and then we can probably take a break. The first strategy is called the epsilon greedy strategy. Okay? Something beyond that round robin and randomly picking an action thing. So this epsilon greedy strategy is now going to start taking into account the feedback we've collected so far. Okay, so it's not gonna, it's not gonna ignore the feedback collected so far. So this is gonna be a departure from A/B testing. So this is where the line between estimating some numbers and decision making has blurred. Okay, and we'll see that in a second. So what is the epsilon greedy strategy? The strategy is any given time index or any given part of the for loop. Let's say you spoke to 50 customers already, as in you showed options and they purchased, not purchased, whatever, happened 50 times. And the 51st time, you need to do something. What do? You say, hey, I have 3 websites, 3 options. With some probability, I'm just going to show something at random. So here I'm just doing exactly what A/B testing would have done. With some probability, I'll just show one of these 3 websites at random. But with some other probability, I'm going to show the website with the highest estimated reward. Okay? I'll have a highest estimated mean reward for one of these websites. Why? Because I have interacted with 50 customers already through some way. Maybe I showed to 16 of those customers, website 1, another 16 of the customers, website 2, and maybe the remaining website 3. I have some sense of what the estimated mean reward is. And one of those estimates is going to be higher than the other. I'm going to show that one. That's called exploitation. Okay. I'm going to show that one with some other probability. Okay. So this is where I'm using the feedback I've collected so far to make a decision. This is the first instance of this. So far, we've not seen the connection between step 2 and step 3 of that online machine learning loop. Now we're doing it because in our action selection step, we're saying, okay, we're going to look at all the feedback in the past, somehow summarize this for each of the 3 actions, 3 of the three website decisions that we have, and pick the website with the highest estimated mean reward. Okay. This is very simple, but still something non-trivial. Yeah.
I'm confused about the difference between reinforcement learning and A/B testing, right? Because it's essentially employing the same criteria where we're doing something, then getting the feedback, then reinforcing that feedback towards our learning.
That's what we're doing here. In A/B testing, we're not. There's no, there is learning. There is some estimation, right? So the A/B testing part, there's an estimation. You collect data,
but it's not continuous. Over here, it's continuous. We're learning, and then we're
yeah. Our feedback is improving our decisions while we are collecting the data. Whereas in A/B testing, you are not thinking about decision. You're just flipping coins, so it's really an ineffective decision-making process. But you're just collecting data. Okay? And then at the end of that data collection process, you're saying one of the decisions is better, and that's only useful for some future use, setting, right? So some future usage. Here, while collecting the data, we are trying to be so we are trying to be more efficient in the sense that if some options are actually, seeming to be bad, let's not even waste our interaction with the customers using those options at all. Like we're kind of doubling down on the more promising options. Okay, so we are trying to be slightly better. I would say not slightly, but we're trying to be better than A/B testing.
So, like implementing sort of reinforcement learning within A/B testing.
Yeah, A/B test is one corner case that motivated us to kind of get away from that and have some sort of, I wouldn't say yeah, we can use the word reinforcement, but basically using the feedback to improve our actions, which is, you can call it reinforcement. But yeah, we're trying to get away from A/B testing to kind of have some sort of a feedback-driven adaptive decision-making process here. And hopefully that leads to some improvement. Okay. I'll show a picture, an illustration in a second. But any questions here? So what is the strategy? The strategy is very simple. With some probability, pick a random action, which is what A/B testing was doing, or any dumb strategy would do. Or you could also do, instead of picking a random action, you could just do round robin. Like, those are all fine. But with some other probability, you pick the subjectively best arm, as in like whichever is currently looking best. Subjectively best means I'll have some estimated rewards, estimated mean rewards for each one of them. Mu hats, let's say, estimates of the true value, which we don't know. And based on those estimates, we can take an action. Right. So yeah, why, what is the intuition, right? Before I show an animation, intuition is basically that to do well, we need to explore all the arms. Okay, the word explore and exploit was first time shown in the previous figure, are a central concept in online machine learning. Okay, this is not there in supervised learning. Okay, the moment you introduce exploration, supervised learning kind of becomes online machine learning or contextual bandits, basically. Okay, so this is a core idea to kind of, you need to gather information. You need to not just rely on currently estimated best actions and just stick with them. Okay, you have to kind of explore. Okay, so you need to explore new ideas and take decisions that you would not take, just to get a sense of how they fare. Okay, while at the same time, you can't just do this, because this would be like A/B testing or something random. You should be doubling down on something which is promising currently. Also, you need to strike a balance between these two. Okay, if an action looks promising, then maybe do more, expose more customers to that website option than the others, for example. Okay, so that's the intuition of why this exploration and exploration together help you achieve some improvement. Okay, what is the improvement? Cumulative regret. Okay, being lower, expected cumulative regret being lower. So that picture is here. Our illustration is here. So let's say there are 5 Bernoulli arms. Okay, instead of the 3 websites, let's say there are 5. Okay, Bernoulli arms just mean when you show that decision with 0.1 probability, there's a sale. Okay, let's say if there's a sale, there's $1, you get $1. So these are Bernoulli arms, means these are the true means of the Bernoulli distribution. Bernoulli distribution, remember, it's one parameter for the distribution. And so let's say these are true means, 0.1, 0.1, 0.1, 0.1, and 0.9. Okay, so one of the answers is definitely much better. Okay, if you knew these numbers a priori, there's no need to do any A/B testing, no need to do maybe multi-arm bandit or anything. Okay, if you know these numbers, you know exactly, oh, take the last action, take the last decision. But we don't know these numbers beforehand. Okay, and exactly that's that's exactly the reason why you would do an A/B test. For example, if you don't know these numbers, you'll have like let's say 5 treatments in one control, or maybe 4 treatments in one control, whichever version you pick, and you'll actually run an A/B test to learn these estimates, okay, so that you can learn that one of them is better than the other. Or you could run a multi-arm bandit algorithm like epsilon greedy. And how does epsilon greedy perform? Right, so it's parameterized by this parameter epsilon. So what this plot is trying to show, before we get into the x-axis and y-axis, is just for different parameters, how does some metric look like? What is this metric? Okay, the metric is x-axis is time. Okay, number of interactions. Okay, so you're going to interact more and more and more with incoming users. And when you're showing these 5 websites now instead of 3, a running example, as a function of time, it's showing what is the probability of you choosing the best website. Okay, the probability of you choosing the best website. The best website is the 5th website, let's say, and you should be choosing the 5th website all the time, ideally, if you knew the information. But by employing the epsilon greedy strategy, the probability of you choosing the 5th website keeps increasing, okay, and gets higher and higher, okay, compared to the probability of choosing any of the other websites. Okay, so you can see x-axis is going up to 0.5, 0.75, and so on. So if you're so you can see that all the curves are above 0.5, for example, which means that you're spending most of the time with the fifth one, because everything else is less than 50% of the time. All these other guys, you're trying out less than 50% of the time. One of them you're trying out more than 50% of the time. Okay, irrespective of what, I mean, given these epsilon parameters. Okay, that kind of shows that you have gravitated towards the right arm with enough number of interactions. You didn't even need these many number of interactions. Its x-axis looks like it goes up to 250. By 50th interaction, you already figured out, hey, let's zero in on the fifth one because that's the most promising. Okay, so you did not waste 100 impressions or 100 interactions. Okay, this is all illustrative, by the way. I mean, these numbers seems low, but in clinical trial, every patient or every person in a study is kind of important and very important data point. So so it gets crucial, like you saving a few interactions to figure out what is the best. Okay. So what is the difference between the curves? The difference is basically if your epsilon is 0.1, then you are not really relying on exploration. You're not trying out new options quite often. So that means that you will learn slowly because you're not trying out what the performance of the other options are. Okay. For example, you might have gravitated towards already towards let's say one of these arms, one of these websites, then you would not try the other ones to learn what their performance is. Okay. For example, let's say you, for some worst case scenario, you kind of gravitate towards arm one because for some reason, although the probability of getting a reward is 0.1, maybe you saw a collection of $1 rewards, because you can flip a coin with 0.1, you can still get a heads few times. Okay. And so it takes some time for you to, because epsilon is 0.1, there's only very few chances where you will try a random action. And so you will not be able to kind of jump away from that and figure out, oh, website 5 is the potentially the better option. Okay, that's why it's a slow start, worse than the others in terms of amount of time needed to start figuring out the best arm. But obviously, once you figured it out, you will be kind of trying it out most of the time. 90% of the time, you will be trying the best arm so far. So you will take the best decision out, most of the time. Whereas the 50% one, even though you figured out what is the best arm, 50% of the time you're trying out a random action. So these are fixed parameters. So you are kind of wasting, quite a few interactions, even though you figured out what's the best one. But there's a trade-off, right? So you don't have to keep them fixed. If you create your own algorithm where epsilon, decays as a function of time, you could probably interpolate between these two curves. So there are many things you can do. This is just a canonical example algorithm. Okay. Any questions? Okay, so I do want to show this some illustration from this blog. So it talks about exactly what we're talking about. So it's a very good resource to look at. But I want to show the animation. So here's the animation. Yeah, let's focus on this figure here. Let's start from the beginning. So this is just showing, I guess everybody examples keep changing. So there are only 4 arms here instead of 3 and whatnot 5. So it's just showing if you randomly pick an action, okay, a slot machine. So this is exactly what A/B testing would do, right? So every incoming data point, you just say, okay, one of these 4 options, let's try. The outcomes are either hollow or filled in. Filled in means you are getting a reward, and hollow means you're not. So you can see that the 4 actions are ordered by their mean rewards, 0.25, 0.3, 0.4, and 0.35. Okay, actually they're not ordered. Sorry for that. I think in the bottom maybe they're ordered, but these are the mean rewards, but we don't know a priori. And so A/B testing is just saying, okay, let's try this, let's try that, let's try this, let's try that. But after that period of data collection, you'll figure out what is the best one because you'll have an estimate, okay, what's the best one. Okay. Let's skip that. Yeah. So they have a section for what's called epsilon greedy. So I'm only directly going to jump to the animation just to kind of keep things kind of focused. Yeah. So here, So what is going on, right? So epsilon greedy, you have to, the algorithm is simple. With some probability, you pick a random action. With some other probability, you pick the most promising one. So here you can see this is the most promising one because it seems like more filled in colors. Actually, yeah, that is. I mean, if you look at the y-axis, you see that third row should be the thing that you should be always taking that action or that decision all the time, and that's what's happening. And sometimes you do take other decisions, and that's because you have an exploration parameter. Okay. Sometimes you try some of the other rows, and and then you get some extra data point of whether that's promising or not. Okay. So the bottom will not make sense right now, but the bottom is just showing some sort of instead of showing a mean estimated value, they're just showing a distribution over the estimated value. Okay? So you can think of some sort of vertical line on those unimodal distributions, and that's our estimate. It may move around, but ideally, let's say theta 0, 1. Yeah. So theta 1 should be close to 0.4, and the other guy should be less than 0.4. Okay, just focus on the estimate. So in epsilon greedy, we are just keeping an estimate of what the mean reward is so far. It'll move around. Okay, it'll not look like this. It'll just be one number per arm. Okay. Any questions about this animation? So all we're doing is illustration of epsilon greedy. No? Okay. So I think the next one is something we will do later, actually right after the break. So let's take a break for 10 minutes and come back at 7:31. Yeah, actually, since we're here, this is a video from 7 years ago. Okay, so NVIDIA back in the day, I mean, was also doing full self-driving. Okay, I don't know if they're doing it today. This is a demo of NVIDIA in CES 2017. Okay, so this is like 7 years ago. They were just showing the capability of the GPUs to be able to kind of process it and learn, infer through vision, and therefore drive the car. I mean, obviously, it's a very, very specific track where there's nothing much going on. And I think the Tesla video was more, I guess, real world. And actually, here's, I don't know if I've shown this video, but this is I guess, more of a marketing video, but they're just showing how the Tesla can go from point A to point B. And this is from a few years ago. And today, obviously, it's possible with some risk. But in this case, it's going from point A to point B, and the person is not touching their wheel. So it's actually doing merging operation on the highway, sticking to the last lane and exiting and going to point B. Right. So all I'm saying is there's a perception problem involved here, in the sense that the supervised learning models are used here to kind of process what's going on in the camera feed, right? But after that, there's a decision-making process. Okay, how much the steering wheel should turn, where to brake, what to do, to put the turn signal on, and all that. They're all decisions, right? So there is I'm not saying it's a completely like a reinforcement problem. There's well-known traditional techniques also part of this, but there's this whole decision-making layer that is kind of enables this, right? And it's not fully solved yet, obviously. Did the person reach, or is it repeating? Okay, they're still driving. Okay, so let's ignore that. Here's another one, and I'll show a couple of more videos later, but maybe next lecture. This is a game. I don't know. Has anybody played this game? Yeah, it's called Doom, and here the agent does in the it needs to make decisions, which is where to navigate and which way to turn and when to shoot. And it has learned to play this game by playing this game again and again and again and trying out different things. So all these things that I'm showing you are just kind of some final versions, but basically they involve exploration exploitation, and we are not there yet. Today's objective, as I said, is like very simple. There's no prediction model, nothing. But next lecture and beyond, we'll kind of understand the basic ingredients to kind of get to this level. Okay. Um, So let me come back here. Oh. Okay, so the next, so what we're going to do is like look at a couple of more, actually 3 more approaches. Okay, why 3 more? Is mostly to kind of completely reinforce the idea that you can do something intelligent beyond round robin, beyond random action picking. Okay, so even if you don't understand like the nitty-gritty details of how the algorithm works, it should be at least first order level. It should be obvious that we are taking feedback into account to pick our next action. Okay, that should be clear. And then if you want to understand the details of why it works, all of these algorithms are all about exactly the same thing. You need to exploit a little bit, you need to explore a little bit. If you don't do either, then you're going to miss out. If you only do exploration, that's just A/B testing. You're just trying out everything without paying attention to how much, what rewards you're getting. If you exploit only but don't explore, you might have converged onto something wrong and you're completely off. And since you didn't try the potentially better actions. Okay, so the next algorithm, it's called upper confidence bound algorithm. Okay, so it's a mouthful, like a huge name, but the name itself tells you what it's trying to do. Okay, so in the sense that it's trying to take into account basically estimates of how good each action is, but also give a extra offset to that estimate. Okay, so what is it doing, right? So this is an algorithm that all these algorithms have to select an arm at any given time. So they select an arm at any given time. How are they going to select an arm? In this algorithm, is going to select an arm based on a bunch of numbers. Okay, there's a lot of indexing here. Ignore the indexing. There's one number per arm that each of these types of algorithms compute. So there's one number. It's just saying pick the arm with the highest number. Okay, that's what this long mathematical expression is saying. Okay, pick the arm with the highest number. What is that number? That number is basically saying that number for every arm is going to be what is my current estimate of its mean reward, like 0.3, 0.35, 0.4, 0.2 that we saw in our animation, our estimate, plus an extra term. And this term is what's giving the name upper confidence bound. Okay, what is the extra term? It looks like, okay, there's a number, there's a log here, there's a time index. So for the 50th interaction, the t is going to be 50. The 100th interaction, the t is going to be 100. So it's just a simple number. It doesn't depend on any rewards or anything. But there's a denominator s, which is the count of the number of times this arm was pulled. Okay? Which is the count of the number of times this action was taken. Okay? So what is happening is that you are doing exploitation by just maintaining this upper confidence bound. Okay, how are we doing exploitation? If this mean reward is high, then the number is going to be high. Maybe we'll try that action, because remember, we're going to try the action with the highest number. So the mean reward is high, probably we'll try that action. Okay, but also that's exploitation. For exploration, even if the mean reward is not high, if number of times I have taken this action is low, this term is going to become bigger and bigger as the time index increases. Like maybe at the 50th iteration, I did not try this action, and this number is some like 0.2 or something. By the time this t becomes, let's say, 100, the numerator has gone up because I did not try this arm. So the second term kind of bloats up if you have not tried that arm. Okay, and so and because of it becoming bigger, there could be some time in the future where that arm becomes interesting enough to try. Okay, so that's how it's kind of balancing exploration, exploitation. It's showing exploration by having this upper confidence bound or a bonus term. Basically, that's why the word B, I guess, for bound or bonus, which kind of increases its value so that you will kind of revisit and try that arm if you haven't tried it. Okay, so that's it. That's the core idea. And all the symbols is just to kind of ensure that, yeah, you're kind of keeping the right average and so on. There's nothing else going on. And that's the algorithm. And we can directly jump to a plot. The plot is just showing the cumulative regret. Remember, lower is better, right? In hindsight, if I know which website is the best one, like the return of 0.4, mean reward of 0.4, then that would, if I try that, then the cumulative reward will be 0. Sorry, cumulative regret will be 0. Regret lower is better. And it turns out, just like it turns out that this algorithm the upper confidence bound algorithm actually comes with a theoretical guarantee, a statistical guarantee on how bad its expected cumulative regret can be. Okay, so it turns out that the expected cumulative regret can only grow logarithmically in terms of the number of interactions. Okay, so the some of the researchers have showed that this algorithm really works, probably works in the sense that it grows, expected cumulative regret grows logarithmically with respect to number of interactions. Okay, why is that interesting? Like, why does log factor or anything like that interesting? Is that if you can show that expected cumulative regret is smaller than, like it's a function of n, which is the number of interactions in the x-axis. If it's a function which is something smaller than n, then if you divide both sides by n, you're saying what is the regret per round? Okay, how much am I off from the optimal thing that I could do? It's like log n divided by n. Okay, as n is large, log n is much smaller than n. So you're saying basically that I'm as good as optimal. Okay, I'm as good as picking the best arm per round. My regret per round is going to be really small. Okay, in the sense that I'm learning. Okay, so that's the it's just a little bit of a tangent on like why we care about curves which go like this. It's just that we want something which doesn't go, the cumulative regret hopefully doesn't grow linearly as a function of interactions. If it grows linearly, something is wrong, you're not learning. Okay. So that's an example for this. And before I jump to another algorithm, I want to show a picture again. This one is, okay. Yeah. So this is a illustration of the algorithm. I mean, it's very hard to kind of make sense of what's going on. I will come to this bottom plot in a second. So even for this algorithm, let's ignore the bottom plot because I will focus on that a little bit and make it's going to become clearer later because this doesn't make sense right now. But here is just showing again that 0.4 is the best one. If you knew beforehand, then you would always try the number one. But since you don't know, you have to jump around, and you can see already that there's more. You're trying out 0, 1, and 2 more than the third one. So you can see that the number of dots you can see is more on the bottom 3 than the top one. Is because you're trying out these ones more, and given the bonus term, depending on where the bonus term is, you kind of switch between which one to show. Okay, so which website to show, which action to take. Okay. Any questions here? Okay, let's look at another algorithm, and that one will have a little bit better explanation of this plot. Let's see. Yeah, it's called the Thompson sampling algorithm. Okay, so another name, but what does it do? It's again, remember, all we need to do is take into account feedback while taking our next action. Okay, so it's a really old approach. At least some variation of this was proposed in 1933, which is a long time from now. But what do we do, right? So what we do is it's a Bayesian approach. Okay, so it's a Bayesian approach, which means that we're going to maintain priors. We'll get an observation. We'll kind of update our prior to get a posterior. We'll get another observation. We'll update to get another posterior, and so on. So it's a Bayesian Bayes rule in action in every time step. Okay. So what do we do at the beginning of the time? We're going to say, hey, I don't know what the mean reward for each action is. Okay, so it's a uniform distribution at the beginning. Then whenever I take that action, I'll get some feedback. Based on the feedback, that uniform distribution is going to become concentrated. It's going to start looking like, oh, where is the mean reward? Where is the mean reward? That's where it's going to become more and more peaky. Okay, so you start with the uniform distribution, and you kind of you do this Bayes updates. Any given point of time, you have a distribution for each of your arms. Okay, the posterior distribution basically. At any given point of time, you would have done some updates for each arm. You get you maintain a posterior distribution for each arm or each decision. And then how do you take an action? You draw a sample from each of these posteriors. Okay, you draw a number basically from, let's say we have 4 arms, we collect 4 numbers, whichever number is the highest, that's the arm I'm going to play. Okay, so very simple logic. All it's trying to do is keep estimates of, hey, where could the mean reward be? And obviously, the more promising the mean reward, if you draw from that posterior, more likely than not, that number will be the highest, and you'll play that one. That's an exploration. That's the exploitation step. But if your posterior distribution is such that even if you know where, even if one of the arms has a really, posterior concentrated on its true mean, which is the highest, there is still a probability that some other arms posterior distribution, when you sample, you might get something from their right tail, and so you might play them. Okay, so it still maintains the exploitation aspect to this algorithm. Okay, so I will not get into conjugate priors. It's just a let me skip that. Let me skip all that. So conjugate priors is just to kind of make the base update simpler. So actually, instead of talking about the base update details, which is kind of a second order detail, I'm going to spend some time on that illustration. Okay, so now it's going to make sense what's going on in that picture. So let me go to the Thompson sampling one. Okay, so now this figure should make sense. The previous figures have an extra, you should read the blog obviously, but they have this bottom part which doesn't make sense for those algorithms. So let's actually start from the beginning. Let's wait for 10 seconds and I'll pause it. Okay. Didn't pause it well, but okay. So what is happening, right? So this is the Thompson sampling algorithm in action. So same for arms, where the mean rewards are not known a priori, or mean sales probability and whatnot. And what you do, so actually a couple of dots already transpired, but if they were not there, you would maintain what is called a distribution over each arm. Okay, so what is this distribution? Distribution over each arm's mean reward. Okay, in Bayesian world, there is no fixed unknown parameter. Okay, although there are fixed unknown rewards for each of the arms, from the algorithm's perspective, it's a Bayesian algorithm, so there's nothing fixed. Okay, everything has a prior and a posterior. Okay, which is your belief on what the true, which is a belief on like what the parameter could be. Okay, so what we do, so we maintain distributions over the true unknown. So maintain distributions over the unknown parameter. Sorry, I keep saying parameter and distribution. So maintain a distribution over the variable theta naught, theta 1, theta 2, and theta 3, because these are now random variables. We're not in the frequentist world, so they're not fixed unknown parameters, they are random variables, and you maintain distributions on them. Okay, at the beginning of time, you maintain a uniform distribution on them. Okay, which means that I don't know where the parameter is. I don't know what the probability of sale is. It could be 0.9, 0.1, whatever it is. So all the distributions will look like this. Okay, even these two will look like that. Okay, I couldn't pause at the beginning. Maybe I should try. Let's see. No, I guess I still have 1 point somehow. Somehow it's not. Yeah. So all of them should be like a uniform distribution. Okay. Now, what do you do? So we can call this prior, but any given point of time, you can call them posterior distributions. Okay. These are just distributions that are placed on the mean rewards, random variables of each of these 4 arms. Okay. Now, let's say I don't know if I can move a little bit. Oh. Yeah. I mean, although it's showing this update here, let's say we played arm 2, okay, and we failed. Okay, we played arm 2, which means we showed website 2, and we did not have a sale. Okay, that's why it's a hollowed out dot here. Okay, if that's the case, then I update my distribution. Okay, from prior to posterior. Because I failed, I need to have pushed my probability mass closer to 0. Okay, that's what I've done here. Okay. And why did I even choose the second arm? Okay, 0, 1, 2, 3. Why did I choose 2? Is because the way we take actions is we draw samples from each one of them. Whichever number is the highest, we play that. It turns out if we draw samples from each one of them, it just ended up that 2 had the highest number because you're just sampling uniform. I mean, they have full fit of any, they can take any number. Just happened to be that this one has the highest number, and so you played this one. You played this one. Outcome was negative in the sense that outcome was not it did not give you any reward. You got $0, and so now you have a posterior distribution which pushed towards the 0. Okay, and so here, I mean, actually, I'm not showing pretty well, but yeah, apparently there were 2 actions that happened, 2 rounds that happened, and you had 1 success and 1 failure, and that's why it's showing some sort of like this posterior distribution is concentrating towards 0.5. Okay, so far we have played 1 action negative, posterior distribution moved this way, 2 actions, 1 positive, 1 negative. So posterior distribution became like this from the initial uniform distribution. Okay. Any questions here? Because when you have a lot of data points, it's unclear what is going on. But any given point of time, all you're doing is, hey, there was a success, there was a failure. Based on success and failure, we know how to update from a posterior to a new posterior, or from a prior to a posterior. That's just base rule. Okay. In fact, the update is easy. I think the slides that I skipped about conjugate priors and so on is about how to make this Bayesian updates without doing the integration. Okay, without doing the summation, integration, whatever is needed. It's possible when you have nice likelihood functions and nice prior and posterior distributions. Okay, when you have beta distributions as priors and posteriors, and the likelihood function is binomial. Sorry, likelihood function is Bernoulli, which is the case for us. Like a sale happened, doesn't happen, or a dot gets filled or doesn't fill. In that case, the posterior still remains beta distributed, and the update of the parameter is just some sort of simple algebraic expression. There is no integration needed. Okay, so any questions here about what's going on in terms of Bayesian approach? How many of you have seen Bayesian approaches before? Where did you see it? Bayesian regression. What was Bayesian in 575? Okay. Yeah, so whatever you do in the frequentist world, like linear regression and all that, there's a Bayesian version of it. Yeah. Okay. So yeah, let me now so now you can see the evolution, right? So θ1 is the best. So you can see it now starts concentrating. θ1 will have better and better positioning, moves around, but its center should be close to 0.4 compared to the worst one, which is 3, which was like not even being tried because its mean is so low that it's not even being tried. Very rarely you might get when you draw a sample from it, you might get a point from here, and so you'll actually try it. Otherwise, you're kind of given up, right? So its mean is so low that sampling a point from it. In fact, it hasn't happened in this video. Yeah, there's something that happened over there. Here, but in general, that's how this algorithm works. So it's exactly the same idea. So use the feedback to kind of balance this exploitation trade-off. Okay, and again, same thing, just like the previous algorithms. Researchers have shown that it has that sublinear, like something, the expected cumulative regret is actually not growing linearly. Okay, that analysis is you have both frequentist and Bayesian analysis, but the point is basically that you can have guarantees on how the regret doesn't grow too big. Okay? The cumulative regret metric that we're talking about. Let's come back. So I wanna cover another algorithm, and why this is because this leads to a very nice connection to contextual Bandit solution. That's one of the key reasons. Okay. So far the algorithms that we've seen are all thinking in terms of I mean, all of them work, by just defining the algorithm we just defined, like maintain priors, maintain posteriors, or maintain those upper confidence bounds and keep changing them. Those are algorithms, but they have guarantees that assume things. Okay, so when you want to say, hey, theoreticians or researchers have given guarantees that the cumulative regret doesn't grow, it's mostly because they make those guarantees under assumptions that the data rewards are IID or rewards come from a distribution and so on. Even when we stated the problem, we said there is a distribution sitting on each decision or arm. Okay, so what we can do instead is to ignore that. Okay, let's drop that assumption. We don't want to assume that rewards have some distributional assumption built in. Okay, so how do you drop that assumption? We say, there are two players. It's going to be a game type of setting, just like GANs. There's going to be two players. Player one is going to select an arm. Player two will pre-select a bunch of rewards for each of the arms, and then based on the arm, I just get to see one of the rewards. Okay, that's a bandit setting. One of the rewards. There's a slightly different setting called full information setting, where you get to see all the rewards, but let's not worry about it. So that's the game. So it's basically adversary picks rewards, you pick an action, you get to see what the reward is. Okay. So in this setting, there's nothing stochastic. There's no expected regret, cumulative regret, and so on. Okay. So in that setting, there is still an algorithm which does as best as you could have done in hindsight. Okay. So in hindsight, if there's an adversary who's picking rewards, they cannot see your action beforehand. Otherwise, they'll pick exactly 0 reward for your action. You can keep getting zeros. So in hindsight, if adversary picks a bunch of rewards, you can always look back and say, hey, what is the best thing you could have done in each situation, in each round, right? Now that number compared to what you did, that gap can be small. That gap can be doesn't have to be too big. Is the guarantee that you can give in this setting. Okay, the algorithm is called EXP3. And it's again, some historical reasons why it's called EXP3, but the algorithm idea is again simple: explore and exploit. And what do? We maintain a number for each arm, just like the UCB case. We maintain one number per arm, and we're going to keep updating this number. Okay, so the more promising the arm is, the higher the number is. The less promising the arm is, whatever the lower the number is. Okay, we're not going to decrease it, but we're going to keep increasing the arm with which has a better performance, better rewards that we collect. Okay, so once we have these numbers, how do we take actions? Very similar to many of the other approaches you've seen. These are numbers. Given these numbers, since these numbers seem to be, they're all positive, it turns out. So we can always normalize them to get a distribution over these arms. Okay, a bunch of positive numbers or non-negative numbers, you can normalize them, right? You can do softmax. You can just do regular averaging. Since they're non-negative already, you can just do number divided by sum of numbers, and you can get a distribution. You can get a probability mass on each arm. Okay, where if the number is high, if W is high, let's say some arm is really promising, then the W will typically be high. And if the W is high, then the probability of choosing the arm is also high. Okay, that probability of choosing that arm is also high. And then from this distribution, you draw a sample. Okay, so a promising arm, more probability of choosing that arm, but less promising arm, it turns out you give a little bit of bump to every arm. So you give an extra constant. Let's think of it as 0.01. Okay? So irrespective of what the W's are, every arm has at least some probability of getting picked. Okay, let's say that's this offset. Don't worry about the symbols here. That's what this offset is. And so every arm does have a fair chance, some chance, not fair chance, but some chance of getting picked. That's the exploration. And the exploitation is, if the arm is really promising, then the W number will be high. If the W number is high, then you're exploiting, basically. Okay, so all I need to tell you is like how are these numbers getting updated by feedback, and that is actually pretty natural as well. So the more rewards you collect, the higher the number should be. There is an e to the power something happening, but that's just some extra transformation. But just think of it as the more rewards I'm collecting, x's are going to be rewards are positive. So bigger the sum, bigger the weight. That's all. There's a minor detail about some normalization, but we are not at that. I'll skip that detail. But that's an important normalization that's happening, some sort of scaling. But I'll skip that detail. I want to get the core idea first, which is we are relying on feedback. Better feedback we get for some arm, the higher the W number, higher the probability mass on that number, so on that arm, more likely that we're going to play that. Okay. Now, contrast all this with like A/B testing, right? There's no such feedback. So far, we've seen 4 algorithms: epsilon greedy before the break, UCB after the break, Thompson sampling after the break, and DXP4 after the break. All of them have simple ideas of how to take promising arms, feedback in the account and play that, but while balancing the exploration. Okay. Any questions here? I know this is a lot of new information, but let me not talk about the synthetic example. But any questions here? No? Is this all too complex? It is basic, right? There's no feature vectors. There's nothing complex going on, but it's just intuition about to be able to explore and exploit to be able to do better than A/B testing. Okay. Because now we're going to get into supervised learning. I know there was one of the goals of the lecture was to say, hey, how is it different from supervised learning? If we don't cover it today, we'll obviously cover it next time. There is a difference between supervised learning, is that we have to do exploration. Even when we did not have features, we had to try actions which we didn't, which didn't seem that promising. But in supervised learning, a model will just say, hey, this is a label, or do a buy, or do a X action if you're going to predict an action. And there's no exploration. Is supervised learning, you can think of it as like a proxy for just doing exploitation, and there's no exploration. So you'll have to do, because there's an exploration, it can be arbitrarily bad. Okay? If it converges on some suboptimal thing based on the current data, then it'll keep doing that, and so you'll get only feedback based on that arm, and so you never know what would have happened if you had tried something else. Okay, so that's the key difference from supervised learning and this, that there is no exploration component in supervised learning. Okay, so for the next 15 minutes or so, I'll talk about contextual Bandit. So so we're getting to reinforcement learning next time. Okay, all the cool stuff that you saw requires some basics, and that's what we're covering today. So we'll cover contextual bandits next, and then talk about reinforcement learning in the subsequent lecture, next lecture, and we'll do a simple code example to show the value of whatever we're learning in the next lecture. At the end of the next lecture, we'll also learn one algorithm called Q-learning. And so we'll kind of see what's the value of Q-learning in a simple toy setting also. Okay. So the last setting, which is the closest to supervised learning, is contextual bandit. Okay. Contextual bandit problem is exactly the online machine learning problem, which is exactly what we saw in the initial motivating example. So the MSN example, they were actually doing the contextual bandit setting. Why? Because they do have the step one. They do get context, they do get feature vectors, they do get user profiles, and then they take actions, and then they get feedback. So far, we've said, okay, forget about features. Let's just talk about getting a reward and just getting a sense of which reward is better, mean reward is better. That itself had the required exploitation. Now, obviously, we'll continue to require exploitation even in the more richer setting. So that's what we'll do. So if you just recall, user errors with the context, we take an action, we get a reward. We want to choose actions to yield higher rewards, like higher sales, for example, in a website example. And the key assumption is going to be that what we show to one user is not going to influence who's the next user who's going to come. Okay, so maybe I show a bunch of sports articles to you, but then the next user who comes, he has no idea that I showed, like, maybe sports articles are not something that you want to see, but he doesn't have that, is not influenced by that I showed you bad recommendations, for example, bad set of articles. Okay, same thing with you yourself. So if you come the next day, you would not remember, you would forget that you had bad recommendations or certain recommendations at the previous time. Okay, so it's like there's no memory in the system. Okay, so it's the same thing with bandits also. There's no, you try an arm, it has nothing to do with the next reward that you get next time you try that same arm. So same idea here. Okay, why is that assumption necessary? It's like saying, okay, in supervised learning, you use training data, you built a prediction model. Let's say you got an image and you predicted cat. Okay, let's say it's wrong. It's not a cat. It has nothing to do with the next image that you'll get. I mean, there's no such mechanism that says, okay, next input that you'll get because you predicted an incorrect answer, I'm gonna influence the next image you'll get. It's not, there's no such machinery, right? So that's what I'm saying. There's no long-term dependence across predictions, decisions, or whatever you're doing here. Here we are doing decisions, so there's no long-term dependence, or there's no dependence across decisions we're making. But still, we need to explore and exploit, because if we don't explore, then we miss the promising decisions we could have made. Okay, so previous models are obviously not enough because there's no context, and there's no carryover effect that I just mentioned. We can capture it in reinforcement learning, so that's subject for next time. Okay, so that's why I keep mentioning the assumption that there is no carryover effect in today's lecture. So what do we do in the contextual bandit problem? The problem is already defined. The online machine learning problem is a contextual bandit problem. Contextual bandit problem when we do have features. So every round we get a context. We want to find best actions. So instead of saying best actions, we can say the best policy now. Okay, so the new word, policy. What is a policy? It's just a function. Why is it a function? It takes context as an input and produces a action as an output. Okay, so it looks exactly like a supervised learning function because there's a feature vector input and you're saying, okay, take action. You can think of actions as classes. So you're doing basically multi-class classification, right? So we want to find, instead of the action, we want to find the best policy, which is like saying, if you find the policy, you will also know what action to take given that context. I mean, it's kind of, in some sense, finding the policy implies getting the right action. Okay. And then this for loop. One of the key features is that we may not see the same context twice. Like in the multi-arm bandit case, there's no context. We can keep trying the same arm. So that's fine. That's on the output, that's on the addition side. But on the contextual bandit side, in the contextual bandit problem, on the input side, we will not see the same context twice. So we may not see the same user twice. Same user profile, for example, twice. Okay? So there's the need for generalization, just like in the supervised learning setting, where you have a bunch of training data, and it's not expected that your test data point is going to be exactly one of these training data points. If it was, then you can just say what the label was, right? Like a dictionary lookup. So you will not, there is a need for generalization. Okay? Yeah, it's different from the bandit setting that we've been seeing because there's no context in the previous settings, as well as we had a single best action. There's no context, right? So there's a single best thing for everybody. So what is the benefit of context, right? So I want to illustrate it through a simple example. What is the benefit of context in the sense, how do you take context into account to learn, okay? To learn beyond like learning and actions quality, right? So in a multi-arm bandit setting, we were just saying, okay, hey, we took an action, we got some reward, we can get a sense of what that action's quality is. Here, we'll take an action, we'll get a reward, and we'll get a sense of how other functions can also do, other policies can also do. Okay, so let me kind of set it up cleanly. So let's say we have 5 ads. Okay, ads, advertisements. Okay, these are the ads. And let's say we have 4 policies. Okay, just as an illustration, this is 4 policies. What do I mean by 4 policies? I have 4 functions. Okay, I only have 4 functions. This is typically not a case in majority of the settings. I don't know in 575 if you've seen a situation where there are only finite number of functions. Did Professor talk about finite number of functions ever? No. Yeah. Okay. So even in the linear regression case, when you have let's say when you're doing ridge regression, the number of functions in your search space is actually infinite, right? So if you're thinking of just doing linear regression, number of functions is infinite because every function is characterized by every bunch of coefficient values, and coefficients, each coefficient is a real number, so you can have infinite number of such functions. Okay, but in the extreme case, you could have only finite number of functions. Let's say there are only 4 functions in our case in an illustration. Okay, what do these functions do? Given the context, I'll say, hey, take one of these ads, show one of these ads. Okay, so our action space is only 5, but there's so many contexts. So let's think of like a multi-class classification setting where some context comes, a function, there are only 4 possible functions, but each function is just saying, given a context, pick one of these 4 actions. 5 actions, sorry. 5 ads or 5 actions. So and we'll kind of build our algorithm by starting with exp3, because you'll see that our new algorithm is going to be just a slight twist on exp3. So what are we going to do for exp3? Let's think of the policies themselves as arms. Okay, in exp3, in the algorithm that we saw a couple of slides ago, actions were the arms. Instead, we can say, hey, instead of maintaining a number per action or decision, we can maintain a number per function. Okay, per policy. Okay, there are 4 numbers to maintain. That's fine. I mean, there's nothing, big difference in, adapting it this way. If so, let's say in round T, the following happens. In round T, policy 1, let's say E1 chooses action 2, add 2, E2 chooses add 2, E3 chooses add 4, E4 chooses add 4. For some, for that given context, these are my 4 policies, and they chose specific adds to show. Okay. And because we were maintaining numbers, remember we were doing exp3, we were maintaining 4 numbers for each of these 4 policies, and one of the policies, let's say E1 got picked because from those 4 numbers, we got a distribution over these 4 policies. We picked a policy. It is E1. E1, we know what add it's going to show for this current context. We just show that add. Okay. And let's say that add was actually clicked, so it's a successful outcome. Okay. So in exp3, what would we do? Since it's a successful outcome, the number or the weight that we're maintaining on that policy will just increase. That's what we do in exp3. So we'll increase it, but with some correction. But that's as I said, even in that slide, in some slide detail, some shifted version, some reweighted version. Typically in exp3, all the other arms will get 0. Okay, because they were not even part of the interaction. Okay, and it turns out we can actually do better than naively applying exp3 in this contextual setting. Okay, what can we do? Because we also observe that the second policy also recommended the same action. Okay, in the illustration in the previous slide. If so, then the reward, we can also ascribe this reward to the second policy as well. Okay? So we are learning better estimates for different policies from the same observation. Okay, this is the benefit of context, where functions which give similar outputs to same context, they all benefit from the feedback. Okay, that's how you can conquer. Otherwise, functions are pretty complex objects. Like if we were struggling in the multi-arm binary setting with like just 4 actions or whatever the number of actions is, to get an estimate and which one is better, it's a pretty hard problem in the multi-arm binary setting. How can we, even tackle the contextual setting? The answer is you have to kind of pool. You have to somehow figure out. You have to exploit the fact that even though there could be 4 policies or even could be infinite number of policies, but the action space is limited. So if I take one of those actions that influences many of these policies, you're also going to predict the same action. Okay, that influences all these policies could be the better ones, the best ones. Remember, our objective is to find the best policy, the policy that does well in all as many contexts as possible. Is that clear or confusing? Okay. So let's look at the algorithm. This is actually very similar to exp4 with a lot of numbers. I apologize for the symbols. Apologize for the symbols. But what we're doing is exactly as before. So we're just going to maintain a weight for each policy, each function now. Okay. Which is exactly what in exp3 we're maintaining a weight per action. Here we're going to maintain a weight per policy. And then in each round, what we're going to do is just do a interesting trick, which is, since we're maintaining a weight over policy, but let's say I only have k actions, like the 5 adds that we could show, I can actually get a derived distribution on these 5 adds. How do I get the derived distribution on these 5 adds? By saying, hey, what are all the policies that are showing add 1? Okay, maybe there are like 5 policies, maybe there are 10 policies which also add 1 for this current context. Then I just add up those weights, and that's going to determine the probability mass on the first add. Okay. Similarly, for add 2, maybe there are 3 policies that are all predicting add 2. Okay. Then I'm just going to add up the weights of these 3 policies, and that's going to determine the probability mass on add 2, and so on. So all I'm doing is, instead of creating a distribution over policies and then again doing a distribution or way on actions, I'm just getting a distribution on actions because they're only finite in number. They're like 5 or whatever is the in illustration there were 5. Then I'm just going to pick, okay, what probably assigned to add 1 is just going to be whatever number of policies, whatever policies we're predicting add 1, those weights I'm just going to add them. And denominator is just going to be weights across all the weights that I'm considering. Okay, so therefore what I get is exactly same as what I got in exp3. I have a distribution of actions, play one of those actions, and once and also I have a little bit of offset so that every action, no action is missed. We don't miss an action, and so there's some balancing for that because we had an extra offset, and that's it. And observe a reward. And once you observe a reward, you update. How do you update? Every policy that's related to the action gets a benefit of this reward. That's all. Okay. So every policy, if it was predicting this action, they get some extra weight. So this is looks like a very messy expression. All it's doing is increases this number. WT this one is just increasing. Okay. Yeah. Any questions that? So the version of contextual bandit algorithm that I showed here is, it's very hard to connect to supervised learning, but behind the scenes, that's what's happening. We are trying to learn functions that map from context to actions. Okay, so it's very similar to supervised learning in that sense. It's a function going from some input vector to an output class label, it's multi-class classification type of thing, except we are willing to do exploration. Okay, we are willing to do exploration, which is not there in supervised learning. Okay? And we need to do exploration, otherwise we will not do well. Okay, and we saw that even without the features situation, when we did not have features, we know that if we were just exploiting and not exploring, then we would have worse performance. We would not. Our regret would be pretty high. We might miss out on what's of other promising actions. Okay, the same idea applies here. We have to do exploration, and that's the differentiating factor between online machine learning and just vanilla supervised learning. Okay, supervised learning itself is a huge number of applications. Among them, if you're doing sequential decision making, where you have the opportunity to kind of get feedback and therefore improve, there you should be you should do exploration. Let me kind of reinforce this idea once more. This is just the last slide. So I'm kind of motivating reinforcement learning, but let me talk about multi-arm. It was just actions and rewards. That's all we were doing. Taking actions, getting a reward, learning what is the best action. Okay, universally best action to do. Okay? That's there is a learning component because a priori we don't know which is the best action, and each action is associated with a number, and we're trying to learn the numbers well enough so that we can figure out what's the best action to take. Okay, so it's very prediction and decision making are kind of pretty tightly coupled. Contextual bandit. Only thing that changed is now there's a state or a context or a feature vector that comes with, like the user comes with a feature vector. Because of that, we are trying to learn a policy which given feature vector picks an action, and that action lets me determine a reward. Not just the action, but also the state or the context together influence the reward. So it's my action and the state of the user, for example, together tell me whether the person bought something or clicked something or whatever, never is the case, for example. So, and what we're trying to learn is this mapping. How to go from state to action. This is a function, like it's like a vector to a class. So this is like, looks like supervisor. Here, there's no vectors at all. So it's just maintaining a bunch of numbers per arm, per action, just figuring out what's the best. Even here, we need an exploitation. So here, certainly we do need exploitation. This is what we are trying to learn. And your action and the user's current profile influence the rewards. But interestingly, let's say you showed something like suboptimal. Let's say the user was is an individual interested in music, and let's say you showed a bunch of sports articles. Okay, you got low reward, right? But next time a user comes in, that if it's the same user, he will not remember that last time you showed he or she will not remember last time you showed them suboptimal actions. Okay, that's the assumption in this model. Now, if you want to get rid of that assumption, you will have to do the full reinforcement learning setting, where your actions, let's say you showed, let's say the person is interested in music, you showed sports that will influence their state. Next time they come, they're like, yeah, this is not, I'm not gonna even come back, for example. They already influence, like if you show sports articles to a person interested in music, they already will give you a low reward. But in the full reinforcement learning case, they might even influence their future interest in your website, for example. Okay, so the future context and vectors that you see will be influenced by the actions that you've taken. Okay, this is very different from supervised learning. Okay? There's another aspect which is like there's no IID-ness. You can't just permute observations, feature vectors like we do in supervised learning. And the other thing is that your actions may not have immediate rewards. Okay, for example, you guys spending Wednesday evening here has no immediate reward. Maybe it's like you're missing your dinner, perhaps. But there is potentially a long-term reward of having a better skill set and hopefully like doing well in the job market or whatever it is, right, in your career. So your actions may not have immediate rewards, but your actions, you can take actions which may lead less reward currently, but might yield higher reward later. Okay? So we'll look at this again in the next lecture. But that's another aspect of reinforcement learning that is not there in contextual bandits or multi-arm bandits, because you take an action, there's no notion of okay, let's wait for like and get the reward later. It's just immediately you get to see for that action what's the reward. Okay. Any questions here? Okay. I think yeah. To summarize, we looked at A/B testing as a way to introduce enhancements, but that we saw that A/B testing is like the simplest situation where there's no forecasting really. It's just getting a bunch of numbers per action. That's looking at which average number is higher or lower effectively. But since that was not very, that's kind of wasteful in the sense that it would have a lot of regret. Okay, it would have in fact what is called constant regret, in the sense out of the two options, one of the options typically will be better. And if so, if you just randomize for those number of interactions, then 50% of the time you've tried something suboptimal. So you have a fixed number of times you've kind of a good share, 50% of the time you've kind of not shown the right thing. Okay. Then we saw multi-arm bandits and contextual bandits. In multi-arm bandits, you can fix that problem. You will not have constant regret. Constant regret means like something which is growing up. Cumulative expected regret is going straight line. Okay, you will not have a straight line. You will have something which is what is called sublinear, and that's what is some algorithms promise that, as in like there are guarantees for that. And then we saw the contextual bandit problem, which is, if you want to informally understand it, it's basically you can do supervised learning, but you have to do exploration. Why? Because you have to learn what you did not try in your data. Okay, you have to know what would be the reward if you did something else. Okay, if you just work with supervised learning, you will not be able to do that. Okay? In the paradigm of supervised learning, you will not be able to do that. And both these bandit approaches are just a special case of reinforcement learning. A special case because you could think of reinforcement learning without any impact on the future next state, or you can say I can ignore the context and just take an action. Then you'll just come back to this contextual bandit setting and the multi-bandit setting respectively. So it's a special case. So we will look at reinforcement learning next time. It is the basics. Okay. Yeah, if you have any questions, please let me know. But we'll kind of stop here.